Hi there, everyone. It's really great to be with you today. I'll be talking about retrieval-augmented generation for web archives. When I use some of the large language models that are available today, and I ask a pretty simple but somewhat obscure question, I get all sorts of different kinds of versions of responses. And here I'm asking Teddy, who's the handyman on Bob's Burgers, what's Teddy's favorite hammer? ChatGPT says quite confidently, Old Hickory. We go over to Copilot by Microsoft. We have Lucky Hammer. That's what it's called. DeepSeek, the one hammer. Very good. I think we're all quite familiar with the fact that right now, in the world of large language models and to a great extent, probably deep into the future, hallucinations are really something that we're not going to be able to get away from. So retrieval augmented generation is something that people have talked about in terms of a way to reduce hallucinations. What it basically does is it retrieves information from a local document store and augments large language model answers using that information. Here you can see this is, it gets a little bit complex, but basically what happens is in a RAG pipeline, you have your reference documents. Those reference documents are, generally speaking, they're embedded using a large language model specifically tailored for semantic search and retrieval. The chunks of the reference documents that are embedded are then stored in a vector database. When a user queries that database, their query is embedded using that same large language model. And that embedding gets that sort of a semantic signature that is then matched to the semantically most similar chunks that from the reference document in the vector database. The chunks of those documents are then combined with the user query and any system prompts, and then that as a big sort of text package is sent off to the to a large language model, something like ChatGPT, GPT-5, whatever it might be. So when I was on my research leave, I started exploring this idea of retrieval augmented generation. The first experiment I did was just basically embedding a PDF document to see what I could do. So in this particular case, it was a PDF document of a book about the Middle Ages. So what I did here was, here's my source document. I used PyPDF, which is a Python library to extract the text from that document, embedded it using this open model from OpenAI, stored those embeddings in a vector store with very little metadata. Over here is my query. The query itself is embedded using the same model. That query is then matched to however many chunks I tell it to match to that are as semantically similar as possible within the vector store. Those chunks are then retrieved. They are combined with my query and my system prompts telling it what to do. And then you can see the answer comes back here. And this answer is, of course, based in the specific context, which is my PDF document here. And so in this particular RAG workflow, I was, started to understand that we could do this. It was possible at a very limited scale. At the same time, a tool from Harvard Library Innovation Labs came along called WARC-GPT, and basically the focus of WARC-GPT was really to see if RAG could be implemented within the environment of web archives. So on my study leave, I started experimenting with it. The document source was this Bob's Burgers wiki, thousands and thousands of pages about this show. And it's relevant in the sense that it's not only a show that I really liked, and so I could sort of myself serve as ground truth, and I could tell if the model or if there was some sort of hallucinations or problems in the pipeline because I had watched the show so much. I was sort of an expert on it, and so the accuracy was something I could measure. But also it represents a lot of non-traditional kinds of source documents that we have in our Web Archives collection. So using Archive It, I generated a bunch of Web Archives files based on this wiki. It consisted of about 12 gigabytes of data, as you can see here, 12 gigabytes. And then started I installed WARC-GPT. You can find this on GitHub, and it's basically just a chatbot. And so what happens is you ask it a question, it provides an answer. These are screenshots from Harvard. You can see here you're able to pick open models. You're able to use an API to connect to things like OpenAI. So you can use like you can use GPT-4, GPT-5, etc. And you ask it a question, you tell it the model that you want to use, some other parameters, and it gives you an answer. And you can see that those answers here are the actual chunks from the vector database that those answers are being pulled from. So what's happening here is these are our source documents here, beautiful soup, which is something that enables us to extract text from HTML and focus just on the stuff that's important to us, so not a bunch of the boilerplate, etc. WARC-GPT out of the box uses the E5 large v2 embedding model and the Chroma vector store. Here's my query embedded with the same model, looked for the semantically similar chunks, augmented those chunks, and you can see here that it could not actually answer my question. So, I mean, one of the really good things here is that it's not hallucinating or fabricating an answer. It is actually telling the user that it can't find the answer, but I know in fact that that information is in the vector store because I could see that particular seed URL in my archived collection. So I wanted to sort of figure out what was happening here and why things were going wrong and see if I could explore that a little bit more. So possible solutions is I wanted to generate machine-friendly work. So when Archived does web archiving, it's really meant to display in the Wayback Machine for users to navigate through that text. And in order to do that, it needs to save a lot of information that isn't really important for a large language model when it's embedding that content. So I wanted to clean up the works. I wanted better text extraction. So I wanted to look at the actual HTML from the Bob's Burgers wiki, determine what tags have the actual content in it, strip out all the other stuff. Try different models, both for embedding the chunks in the vector store and also for text generation at the end. And then refine some of those embedding strategies in terms of how big the chunks are, how big the overlap is between the chunks, and all sorts of really technical bits that I won't get into now. And then, of course, the prompting strategies, which are a hugely important thing in anytime you're interacting with large language models, how you prompt it to answer. And so what I built was a very simple web app using Python and Flask that was enabled me to enter a query. It enabled me to customize the number of chunks I wanted retrieved, and then I was also able to tweak my system prompt here that would be bundled up with the chunks after they were retrieved and then passed on to the large language model, telling it what to do. And then I could also see the chunks that things were directly coming from the source documents. And what I was able to do, so I'll show you here. Here's the original source documents. Again, these source documents were stripped down from about 12 gigs to a couple gigs maybe, just by finding the beautiful soup extraction scripting using the E5 large V2 model, a Chroma vector store again with some metadata in there as opposed to the face vector store, which I used originally. I was able to ask my question and get the answer. So you can see here the McLachlan hammer. So the other thing I changed here was instead of using an open model, I used the OpenAI API and used GPT-4, cleaning up the data, chunking things more effectively, using better system prompts, more fulsome system prompts, and a state-of-the-art frontier model for generation. And I was able to step through the RAG pipeline and the workflow there to get much better answers. Now, I'll just say that within WARC-GPT, you can actually look into the code and do a lot of that tweaking without having to build your own thing. I wanted to build my own pipeline just out of interest and curiosity, and it would also give me a better sense of what we would actually need to do within a library setting if we wanted to deploy something like this in the future in production. So a lot of the variables in the RAG workflow include source document quality. So if you have really noisy web archives, you're going to get poor quality. You need to think about which models not only are you using to embed your original source documents into that vector store that you're then going to semantically match with your user queries, but also for the generation of the answer. So the frontier models that you're going to be using for answer generation at the end. Chunking strategy is really critically important. It's a bit of a technical issue I won't get into here, but prompt design is also critically important. The really critical thing here, I think, to remember is that there is the ability to do this within a research library setting using open tools from the beginning to the end. All of these tools here that can be used to build a RAG pipeline, fully encapsulated, so running on local machinery. Some of the limits here for what I'm calling naive RAG is that it's a pretty brute force thing where you're trying to match, semantically match your query with a bunch of chunks in a vector database. And depending on how you've chunked those things up and the noise inherent within your original source documents, it can be really problematic. Because those chunks are not token by token retrieval, you can miss the sort of the needle in the haystack. You can miss exact entities. And the algorithm that's used to match those can be quite brittle. So there's all sorts of issues with RAG in the simple implementation that I'm showing you here. And there's all sorts of ways that people have tried to improve that, including hybrid lexical and dense retrieval. So that's basically using semantic search with the embeddings, but also just standard keywords, and then re-ranking for relevance, using something like GraphRag, which recognizes entities, and feeding metadata into the retrieval process is also really critical. There's a lot of technical complexity here. There's the costs if you're using frontier models via API. Expertise is an issue. The reliability of the RAG pipeline can also be an issue. There's still going to be hallucinations sometimes. So is this ready for actual wide release? And also sustainability when we build these workflows and these pipelines and things are changing so much. How do we sustain those appropriately? So I think looking ahead, it's critically important that we pilot this type of stuff, we explore it, and knowing that there are a lot of open source tools that are maturing quickly. And so I think, in the next year, 6 months, 2 months, who knows, there's going to be things that come up on GitHub and in the community that are going to help us do this. And we really need to share not only infrastructure, but expertise across our institutions. So thanks so much for listening. And for those of you that would like to dig in further, here is a link to my study leave report that gives you everything in detail. I look forward to your questions.